In this lecture, we'll look at the two main problems in dynamics of multibody systems. The first is the inverse dynamics and the second is the simulation of equations of motion. So there are two main problems in dynamics of multibody systems. The first is called as the inverse dynamics. In the inverse dynamics problem, we are given the geometry and inertial parameters of all the rigid bodies in a multibody system, and we are also given a trajectory as a function of time. So what I mean by trajectory is we are given the generalized coordinates q as a function of time, q dot as a function of time, and q double dot as a function of time. And the goal in the inverse dynamics problem is to obtain the torque which must be applied at the joints so as to get these q of t, q dot of t and q double dot of t. In the direct problem, on the other hand, we are given the kinematic and inertial parameters and the joint torques as a function of time. So we are basically given tau of t as a function of time, and the goal is to find the trajectory of the rigid multibody system. So the goal is to find q of t, q dot of t and q double dot of t. So as you can see, it is in some sense opposite of the inverse problem. The inverse problem or the inverse dynamics problem is required for sizing of actuators and model-based control, as I have mentioned earlier. So once I know that the multibody system should be able to have a desired trajectory given by q of t, q dot of t and q double dot of t, we need to choose the motors and the actuators in the multibody system. So we need to solve this inverse dynamics problem to get an estimate of the torque required to achieve this q of t and q dot of t and q double dot of t. So hence the solution of the inverse dynamics can be used to estimate the size of the actuators. It is also used in model-based control. The direct problem, on the other hand, is required for simulation. So if I make a model of my multibody system and if I tell that the torque which you are applying at the actuator is given by tau of t, I need to show you how the rigid bodies of this multibody system are going to move. So hence we need to solve the equations of motion, and that is called simulation. The inverse dynamics problem in multibody system is relatively simple. It is actually quite simple. All we require to do to solve the inverse dynamics problem is to take this q of t, q dot of t and q double dot of t in the right hand side of the equations of motion. So we have an equation of motion which is given in this form. Tau is some mass matrix into q double dot plus c into q dot, gravity term. There might be also be a friction term. All we need to do is substitute q of t, q dot of t and q double dot of t on the right hand side and evaluate torque as a function of time. So the left hand side is nothing but, after substituting this q of t, q dot of t and q double dot of t, we get torque as a function of time. So as you can see, it is a relatively simple problem. It can be done for any multibody system once the equations of motion are known. So once the right hand side or the full equations of motion are known, the inverse dynamics problem is nothing but simple substitution. That is why I said that the inverse dynamics problem for multibody systems are very simple. It can be done very efficiently. So it can be done, for example, in ON steps using the Newton-Euler algorithm, which we have looked earlier. So we can start with the base. We can substitute q of t, q dot of t, q double dot of t, and find all the terms on the right hand side as we go up to the final node, and then we can come down and find the torque as a function of time. So it is a linear complexity algorithm. So let's take an example, and again we will use our simple example, which is the planar 2 degree of freedom two rigid bodies connected by two rotary joints. So there is a link 1 and a link 2, and again the link 1 is specified by mass, length, location of CG and inertia. Likewise, link 2 is specified by mass M2, L2, R2 and I2. Again, I2 is the Z component of the inertia, which is of relevance here because this is a planar motion. So to solve the inverse problem, we need the numbers for the geometry and the mass properties. So in this example, I have assumed that the length of this link is 1 meter. The length of this second link is also 1 meter. The mass is some 12.456 kg. This is from some actual example which we considered long time back. The location of the CG of the first link is at 0.773 meters from this origin, and for the second link it is at 0.583 meters again from this origin, and the inertia is 1.042 kg meter square. Each link has the same geometry, it is made of the same material, and hence the inertia about the z-axis about the CG are same. So for the mass, inertia and geometry parameters which were shown in the table, we can now solve the inverse dynamics problem. So the next thing that we need to solve the inverse dynamics problem, we need to choose a trajectory. And in this example, we have chosen a circular trajectory, meaning that the tip of this 2R manipulator or rigid body chain with 2 degrees of freedom will trace a circle which is given by x equals a plus r cosine phi, y is equal to b plus r sine phi, where a and b are the center of the circle and r is the radius of the circle. Okay, so it will be some circle which is located somewhere in this region. And to find out actually what the circle is and where the circle is, we need to choose some r, a and b. And again in this example, I have chosen r as 0.2 meters, a as 1.2 and b as 1.2. So the center of this circle is somewhere here, okay, 1.2 here and 1.2 here, and it is a circle of radius 0.2. To bring time into the picture, we need to now specify how does this tip of this robot traces the circle in how much time. So that can be specified by saying that this angle phi in the parametric equation of the circles goes from 0 to 2 pi in 10 seconds. Okay. So here is a picture of the circle which it is actually going to trace. So this is very straightforward computation. You substitute phi going from 0 to 2 pi. We substitute r, a and b in these equations and we trace this circle. So in the previous slide, I showed you that the tip of this robot will trace a circle, okay, of radius 0.2 and located at 1.2, 1.2. Now, to solve the inverse dynamics problem, we need to find theta 1 and theta 2 as a function of time. We also need to find out theta 1 dot and theta 2 dot, and also the second derivatives of theta 1 and theta 2 as a function of time. Because remember, the equations of motion are tau equals some m into theta double dot plus some Coriolis term plus some gravity term. We have specified the trajectory using x and y, but I need the trajectories in terms of theta 1 as a function of time and theta 2 as a function of time. How do I obtain this? We can obtain theta 1 and theta 2 as a function of time by what is called as inverse kinematics. So basically this can be done analytically, and all we need to do is we need to take the kinematics equation, which is x equals L1 C1 plus L2 C12 and y equals L1 S1 plus L2 S12. So we have two equations in two unknowns. We are given x and y. We have to solve for theta 1 and theta 2. So remember, C1 means cos theta 1, C12 means cos theta 1 plus theta 2, S1 means sin theta 1, S12 is sin theta 1 plus theta 2. So we can solve these two equations in two unknowns by doing some tricks. So basically, if you do x square plus y square minus L1 square minus L2 square, then you will get theta 2. So theta 2 is cos inverse of this quantity divided by 2 L1 L2. Theta 1 can also be found once you find theta 2, and that is given by a tan 2 of y comma x minus a tan 2 of L2 S2 comma L1 plus L2 C2. Okay, so this, what is a tan 2? This is a function which is like tan inverse of y by x. However, a tan 2 is giving an angle in the right quadrant. We had seen this a tan 2 when we were doing Euler angles, and that is exactly the same thing that we are using here. We want to obtain the correct angle in the correct quadrant. So tan inverse of minus 1 comma minus 1 will give you 45 degrees, but a tan 2 of minus 1 comma minus 1 will give you in the third quadrant. The expression for theta 1 dot and theta 2 dot can also be obtained analytically. So basically we take the derivatives of these two equations. We have x dot, then we will see this will be minus L1 S1 theta 1 dot minus L2 S12 theta 1 dot plus theta 2 dot and so on. And then we can solve theta 1 dot and theta 2 dot in terms of x dot and y dot, and that is given by this expression. You can verify it yourself, that theta 1 dot theta 2 dot is 1 by L1 L2 S2 into some matrix which contains L2 C12 L2 S12 minus L1 C1 minus L2 C12. So this is the first column, and the second column is L2 S12 minus L1 S1 minus L1 S12. Okay, and then we multiplied by x dot y dot. So we can obtain this expression for theta 1 dot and theta 2 dot. So this is actually L2. The expression for theta 1 double dot and theta 2 double dot can also be obtained from the expressions of the derivative of x dot and y dot. So now that we have expressions for theta 1 and theta 2 as a function of time, likewise theta 1 dot and theta 2 dot as a function of time, and theta 1 double dot, theta 2 double dot as a function of time, we can go back and look at the equations of motion which are given here. So we have tau 1, tau 2, some matrix into theta 1 double dot, theta 2 double dot, and then this Coriolis and centripetal term which have theta 1 dot square and theta 1 dot theta 2 dot and so on, and then the gravity term which contains m2g L1 C1 plus R2 C12 and so on. So functions of angles theta 1 and theta 2 as a function of time and gravity. So we have now obtained theta 1 as a function of time, theta 2 as a function of time. All we need to do is substitute in the right hand side of this equations of motion. So if you substitute theta 1 as a function of time and theta 2 as a function of time, everything inside this matrix is known. Then we multiply theta 1 double dot as a function of time with and theta 2 double dot as a function of time with the relevant elements of the mass matrix, and we can evaluate this term. So we can write one code in MATLAB where you give the inputs, which are theta 1 theta 1 dot, theta 1 double dot, theta 2 double dot, theta 2 dot as a function of time, and then you substitute here and we get tau 1 as a function of time and tau 2 as a function of time, which is the inverse dynamics problem. So here are some plots for that circle which I showed you. Theta 1 varies in this form, theta 2 varies in this form, theta 1 dot and theta 2 looks like this. So the blue one is theta 1 dot and the green one is theta 2 dot, and so on. And then we can also obtain theta 2 double dot and theta 1 double dot. So it's not very important to see what are these numbers, but this is over a period of 10 seconds. The x-axis is 10 seconds and the y-axis is, in this case, it is theta 1 double dot and theta 2 double dot. So as you substitute back in the right hand side of the equations of motion, we can plot tau 1 and tau 2 as a function of time. So you can see that the tau 1 is maximum tau 1 is of the order of 170 Newton meter. The maximum tau 2 is of the order of 70 Newton meter. These numbers are not important, but basically what I'm trying to show you is for a given theta 1, theta 2, theta 1 dot, theta 2 dot, theta 1 double dot and theta 2 double dot, basically the trajectory of this multi-body chain, in this case 2R manipulator, I can find out the torque required to achieve that trajectory. You can have many different trajectories, and for every single trajectory you can obtain tau 1 and tau 2. And what is the estimate, or which motors will you choose? You find out which is the worst case. So you find the maximum tau 1 and maximum tau 2, which you get for all the possible trajectories that you can think of, or all the trajectories which this 2R robot is planned to be used for. And then you can get an idea, okay, I need so many Newton meter torque for the first motor and so many Newton meter torque for the second motor. So next we look at the simulation of the equations of motion. So simulation is exactly the opposite problem. This is also the direct problem. In simulation, we are given the external torques and forces and we obtain the motion of the multi-body system. Okay. So in this case, tau 1 and tau 2 as a function of time will be given to us for this 2R chain, and then we have to find out what is theta 1 as a function of time, theta 2 as a function of time, and so on. So how do we do this? We go back again to the general equation of motion of our n degree of freedom multi-body system. So we have this equation of motion, which is torque equals mass times q double dot plus Coriolis centripetal term plus gravity term plus some friction term which we have added in an ad hoc manner. So in simulation, we are given the left hand side as a function of time. We are given tau as a function of time, and we have to find out q of t by solving these differential equations. So these are n coupled nonlinear second order ordinary differential equations. Coupled because remember the mass matrix contains, even for the 2R case, contains theta 2. These have theta 1 dot square and theta 2 dot square and all possible combinations. So for the 2R manipulator example, both the equations were coupled, and these are also nonlinear because you have sine theta 2, cos theta 2, and so on for the 2R case. Okay, cos theta 1 plus theta 2, and then something like sine theta 2 into theta 1 dot square. So all kinds of nonlinearities is there in these equations of motion. So for most of these cases, we cannot solve it analytically. Okay, differential equations are very hard to solve if it is nonlinear and coupled. So only for maybe some very, very simple case, okay, we can solve these equations of motion. Basically, we can integrate those equations of motion given the left hand side as a function of time, we can find q as a function of time. So that is most of the time, or in fact actually almost everywhere, it is not possible to do analytically. So we need to do numerically. Okay, so the numerical solutions of ODE are very well known. It is a very again a very mature topic. There are many software tools which are available, and we are going to use MATLAB. So in this NPTEL course, you have access to MATLAB, and you can try getting some numerical solutions of the differential equations. So we will give at least one homework where you can solve this numerically, this differential equation, to see what is the solution or what is the simulation of a multi-body system. So MATLAB gives you inbuilt integration routines such as ODE 45. Okay, so if you see the MATLAB tutorial, which is written by one of the TAs for this course, you can see he has used ODE 45 for some solutions, okay, for some solution of certain differential equations. So please get familiar with ODE 45. So the input to ODE 45 is required to be in the state space form. So what exactly is the state space form? We want the differential equations as a first order equation. So basically we want it in the form x dot equals g of x comma tau. So this right hand side could be nonlinear functions of x and also torque. So but the equations of motion are second order because they contain theta double dot. So but we want everything in the form of a first order equation. This is what ODE 45 requires you to give. So basically ODE 45 requires you to give what is the right hand side of this first order differential equation. And it also requires you to give some initial conditions. So we need to say what is the solution at t equals 0. All integration routines require an initial condition. Even analytically, if you want to solve or integrate, okay, then you need some initial conditions. So how do we convert the second order ODEs into the state space form? Okay, so how do we do it? We start with the equation of motion, which is mq double dot is t minus c minus g minus f. So we know that the mass matrix is invertible. So hence we can always write q double dot as m inverse t minus c minus g minus f. So f is the friction term, this is the gravity term, this is the centripetal Coriolis term, and this is the external torque. Next we define x, which is, so it's an element twice the number of q's. Okay, so we have x1 through xn as q1 through qn. So remember, we had theta 1, theta 2, theta 1 dot, theta 2 dot. So we need to say x1 is q1, x2 is q2, or x1 is theta 1, x2 is theta 2. And then we write x3 and x4 as theta 1 dot and theta 2 dot. So in general, what we have is x1 through xn are the generalized coordinates q1 through qn, and xn1 n plus 1 to x2n are the derivatives of the generalized coordinates. So we had n q's and n q dots. So hence we have x, which are 2n of them. Okay, and then we write these n second order ODEs as 2n first order ODEs. Okay, and how do we do that? You can see that the x1 dot, which is nothing but q1 dot, is same as xn plus 1. Okay, similarly x2 dot, which is q2 dot, will be xn plus 2, and so on. So xn dot will be x2n. And what about xn plus 1 dot all the way to x2n dot? That we can obtain from this equations of motion, which is m inverse tau minus c minus g minus f. So instead of writing it as q and q dot, we can write at c as of x. This tau is a function of time, so it's not a function of x. But gravity could be a function of q, but it is not a function of q dot, but nevertheless we write it as g as a function of x. The friction will be a function of both q and q dot, which is a function of x. Remember, there are 2n of these x's. So we have n first order equations of the form x1 dot is xn plus 1, x2 dot as xn plus 2, and so on, and then xn plus 1 dot all the way till x2n dot as equations of motion, which is m inverse t minus c minus g minus f. So we have converted the second order equation, n second order equation, into 2n first order equations. This is a very standard technique, but those of you who have used it should be familiar. But otherwise, it is very easy to convert a second order equation into 2 first order equations. So hence, if you have n second order equations, we will get 2n first order equations. So for parallel systems and closed loop mechanisms, the equations of motion are a little bit more complicated. So we have mq double dot is f minus, remember this psi constraint matrix, psi m inverse, psi transpose, and all those things, where f now denotes t minus c minus g minus f. So again we can obtain 2n plus m first order equations, because here the number of equations after elimination of lambda, which is this, is n plus m. So when you convert it into first order equation, we will get 2 into n plus m first order equations. And again, it is very easy. x1 dot is xn plus m plus 1, x2 dot is xn plus m plus 2, and so on. And xn plus m plus 1 dot all the way till x dot 2 into n plus m are obtained from this equations of motion. Okay, and again this f denotes tau minus c minus g minus f. So it is a very reasonably straightforward approach of converting n second order ordinary differential equations into 2n first order ordinary differential equation. In the case of parallel systems and closed loop mechanisms, we have 2n plus m first order equations. The nature of the ODEs, however, are quite different from the ODEs obtained from serial chain. Let's elaborate a little bit on that. So we started with m loop closure holonomic constraints which needed to be satisfied. Remember, we had broken this 4-bar linkage at some point, and then we went from one side to that point, and we went from the other side to the point, and we have equated the x and the y coordinates. So they were loop closure constraint equations. They were holonomic. Okay, so what we have inherently is a set of differential equations and some holonomic constraints, okay, which involve only the position, x, y, theta 1, theta 2. They do not contain theta 1 dot and theta 2 dot or theta 1 double dot and so on. So these are called as differential algebraic equations in numerical analysis. Okay, and DAEs are not the same as ODEs, and I don't want to go into full details, but DAEs are what are called as inherently stiff equations. Okay, so basically what you need to do is, you can most of the time you can get away with ODE 45, but for some set of differential equations or differential algebraic equations, you need to use what are called as stiff solvers, and MATLAB gives you these stiff solvers. So this ODE 15s is a way to solve stiff differential equations. So ODE 23s is another such product or another such package or another such routine which are given by MATLAB to solve stiff equations. So please take a look at MATLAB reference material and see how ODE 15S or ODE 23S is really different from, let's say, ODE 23. Okay, there is a ODE 23 also, and there is an ODE 23S. So what is the difference? You can see yourself. So stiff solvers in general, broadly speaking, they use what are called as implicit schemes. Okay, and they are slower than non-stiff solvers. Okay, anybody who knows what is implicit should know that the opposite of implicit is explicit. Okay, in an explicit scheme, you can march forward in time. In an implicit scheme, at every point you have to solve a set of linear equations. So hence, they are slower than non-stiff solvers. For simple problems such as the 4-bar mechanism, ODE 45 works fine. So we don't have to use any of the stiff solvers, but you can try. It is very easy to change in a MATLAB code from ODE 45 to, say, let's say ODE 23S. Okay, all you need to do is wherever you are calling the solver, ODE solver, you can change from ODE 45 to ODE 23S. Nothing much needs to be changed. And then you can see what happens when you solve a differential equation with ODE 45 as opposed to a stiff solver. So let's continue. In parallel configurations, there is also another big difference, which is the following. So actually what we want to solve is this eta of q comma t equal to 0. So this is the actual loop closure constraint equations. However, what we have actually done is we have taken the derivative of this and then the second derivative of this, and we are using the equation after taking the second derivatives to eliminate the Lagrange multipliers. So we are actually solving the constraint in this form, not in this form. And what is the difference between these two? What you can see is instead of eta of q comma t, suppose you have eta of q comma t plus c1 plus c2t equal to 0, where c1 and c2 are some small numbers. So when you take the second derivative of eta plus c1 plus c2t equal to 0, what you will get is this. So any small changes, numerical errors in q double dot due to integration will cause increasing q dot and q, because you are not solving this, you are solving actually this. Okay, so what you will get is not eta of qt equal to 0, but it is possible that you are using eta of q plus c1 plus c2, and this c1 c2t, okay, if c1 and c2 are increasing with time, so the actual eta of q equals 0 will not be satisfied. Okay, and this c1 and c2 can arise always due to the numerical solvers. Okay, so we are using some numerical techniques to solve the differential equation, so it will never be exactly satisfying the constraint equation. So it will be some small changes, and because we are using the second derivative, we will slowly grow with time. So Baumgarten in 1983 proposed a way to actually try and solve for eta of qt equal to 0. Okay, so what he said is we replace the second derivative constraint equation, which is this, with something like this. So instead of psi q double dot plus psi dot q dot plus phi dot of t equal to 0, we will replace it as psi q double dot psi dot q dot plus phi of t. So this is one term, plus some 2 alpha times phi of t psi of q dot plus some beta square eta of q comma t. Okay, so if you look carefully, this sounds or looks very much like a spring mass damper system where alpha and beta are constants. So this is like x double dot plus 2c x dot plus this is omega square x. Okay, so if you choose alpha and beta, just like in a spring mass damper system properly, the oscillations die down. And what is oscillation here? Which is x double dot, x dot and x. Okay, so if you choose alpha and beta properly, then x will go to 0, x dot will go to 0 and x double dot will also go to 0. In a spring mass damper system, if it is damped properly, it will x dot, x double dot, all of them go to 0. Okay, so that is what he suggested, that instead of trying to use this equation to find the Lagrange multipliers and finally find the equations of motion, we will use this equation. Then the question comes, how do we choose alpha and beta? Or you might say that it looks like a spring mass damper system, but it is not really a spring mass damper system. This is nowhere like mx double dot. This is nowhere like cx dot, or this is nowhere like kx. Okay, because it is a very nonlinear function. But nevertheless, it's a reasonably good idea. If I play around with this alpha and beta, I can ensure that not only eta of q comma t is 0, but eta dot of time will also go to 0. So all of them will go to 0. Okay, and hence the loop closure constraint equations are exactly satisfied, are 0. So this is called Baumgarten stabilization. So the errors in the loop closure constraint equations will not grow with time, because they, as t tends to infinity, they will go to 0. But it is not very clear how to choose alpha and beta. You have to play around with alpha and beta. Let's take some examples now. So another example is that we have worked on earlier, which is called the spring pendulum. So basically we had a mass here which is mounted on a spring. The free length is L, and then once the spring is compressed, we have a force which is K into R minus L, and there is gravity acting, and then there is these components mg sine theta, mg cos theta, and also we have this centripetal term and we have this Coriolis term. So in order to solve these equations, we have two equations, basically two ODEs. Okay, and then we can write down these ODEs, and we need to now find out some numbers for the mass of this bob, spring stiffness, free length, and some initial conditions. So for the example, we are assuming that the mass is 2 kg, the spring stiffness is 15 newtons per meter, the free length is 5 meters, and initial conditions are, r is 5 meters, theta is pi by 4, r dot is 0.1 and theta dot is 0.2 radians per second. And we will also compute the various components of the acceleration just to show how they are changing with time. So both of these two equations can be converted to first order ODEs, and then we will use MATLAB ODE function to solve these differential equations. So here is a video of this spring pendulum. And you can see this animation of this mass, which is the bob, as it is going around. Okay, so what you can see is the spring is lengthening and shortening. Okay, so unlike a pendulum, there is a spring which is here, and the spring can go in and out, and this mass can also go in and out. So this is a simulation which is obtained after solving those two differential equations. Okay, and as I said, I want to plot the various acceleration just to get a feel for what kind of numbers we are talking about. So the Coriolis acceleration from 0 to 20, which is the motion of this bob, looks like this. Okay, the centrifugal acceleration, which is L theta dot square, and this is 2 r dot theta dot, and this is r theta dot square, looks like this. And the tangential acceleration, which is theta double dot, looks like this. So what you can see is this Coriolis acceleration is maybe slightly smaller. The tangential acceleration is probably the largest. Okay, of course, this is because we have chosen some k, m, r, and so on. Okay, if it is some other values, maybe these plots could look differently. But the point is, we can take those two differential equations, we can use ODE 45, and we can find out the motion of the bob, which is what I showed you in the video. Not only that, we can find out the velocities and accelerations. And I am showing you 3 of the components of the acceleration. Let's continue. Now we will see how we can simulate the motion of a planar 2R robot. Okay, so we had this 2R robot. The first link was M1, L1, R1, I1. This is the location of the CG. There's a torque which is acting, gravity is acting this way. There's a tau2 which is acting on the second link. Okay, exactly the same, nothing new. And we can have these equations of motion, which is tau1, tau2 is given by some mx2 and cx and gx2. Okay, so why x2? Because it is only theta 2 which is important, whereas the Coriolis term contains theta 1, theta 2, theta 1 dot, theta 2 dot, which is what this vector x is. The mass matrix is only a function of theta 2, which is why I have written it as mx2. So this is a 2 by 2 matrix, which is a function of only theta 2. Remember, theta 1 was x1, theta 2 was x2, x3 was theta 1 dot, x4 was theta 2 dot. Okay, so the state variables are x1 is theta 1, x2 theta 2, x3 theta 1 dot, x4 theta 2 dot. And we can write it in the state space form, which is x1 dot is theta 1 dot, x2 dot is theta 2 dot, x3 dot, x4 dot is this. Okay, so we have written it in the state space form. So actually theta 1 dot, we have to write it as x3. Okay, theta 2 dot, we have to write it as x4. So because we want the state equations as g of x comma tau to be equal to 0. So we have written it in the state space form. So once we have those 4 first order equations in the required state space form, we can give some initial conditions. So for this simulation, we are choosing theta 1 as minus 90 and theta 2 as 45 degrees. So what does it mean? This link is hanging down because it is minus 90. So this angle is minus 90, and then theta 2 is 45 degrees. So we have a link which is hanging down, and the second link is like this at an angle of 45 degrees. And there is no torque. Okay, again, just to illustrate that we can solve all kinds of differential equations, we have chosen, this is a nice interesting case. These are that there are no external torques. We can put tau 1 and tau 2 as 0. So it is like a double pendulum. Okay, so we have this pendulum, one link, and then the second link. So the first link is hanging vertically down, and then we displace the second link by 45 degrees, and then we let it go. So I want to see what is the motion of these two links. So in order to solve these differential equations, we need numbers. So again, we have assumed length is 1 meter, mass is 12.456 equal, CG is this, and inertia is 1.042. So these are the same numbers which were used for the inverse dynamics. So here is a video of the 2 degree of freedom robot. So as I said, our double pendulum, as I said, we'll put the first link down and the second link is rotated by 45 degrees and then we leave it. Okay, so as you can see, the motion of the tip is quite complicated. It is not like a simple arc of a circle. It is going forward and doing all kinds of loops and then it is coming down. Okay, so I'm not sure how many of you expected that it will do all kinds of crazy motions like this, but double pendulum actually does motions like this. Okay, and I can clearly see that for this special case of this link length, which is 1 meter and 1 meter and no external torques and the CG located at some places, this is the motion of the tip. I could have also plotted the motion of any other point on this link or any other point on this link. You know, MATLAB, once you find θ1 as a function of time, I can find out what the CG is doing. Okay, what is the CG? This is the distance R1 along the link. So we can plot what is CG is doing. We can also plot actually θ1 and θ2 as a function of time. So what you can see is θ1 is doing all kinds of things like this. So it is not a simple harmonic motion, you know, although we should not expect a simple harmonic motion like a sine wave. The second link is a little bit more periodic, because again it is not, because what you can see is the amplitude is changing, okay, as we go along. The first link is definitely doing, you know, interesting things. So why does this happen? Basically what is happening is the two differential equations, they are coupled. So once you leave the second link, the motion of the second link causes a motion of the first link. Remember, we started with θ2 as 45 degrees and θ1 as minus 90 degrees. So it is vertically hanging down with second link displaced by 45 degrees. So when you leave the second link, it will start oscillating, but then due to the motion of the second link, the first link will also start moving. Okay, and that is the nature of this coupled ODEs. And the path traced by this tip of this second link is, as I showed you, it is quite complicated. And we can solve the equations of motion and exactly show you what the tip motion is. So we started from somewhere here and it went down and it went this and did all kinds of strange motions. We can also simulate the 4-bar mechanism. So we have derived the equations of the 4-bar mechanism. Okay, and what I'm going to do is we are going to place the 4-bar mechanism in this almost folded configuration. Okay, so the first link, fixed link is this, the second link is this way, the third link is this way, and the fourth link is this. So this is exaggerated a little bit, but basically all the 4 links are lying on along the x-axis. This is called as the folded configuration. The initial θ1 and phi1 are small, so it's a little bit exaggerated here in this drawing. And what you can see is, you can do some simple calculations, that if you choose L1, L2, L3 and L0 in a particular way, eventually this mechanism, and if you start to rotate L1, okay, after some angle, the rotation θ1, it will stop and it will form a triangle. Okay, that is the reason why, because L1 and L2 and L3 and L0 are chosen in this way. Okay, so that it cannot rotate beyond this some angle θ1 because it will form a triangle. So in the actual simulation, we will assume that this θ1 is rotated by means of a torsion spring. Okay, so theta 1 is actuated using a torsion spring. The right hand side of the equations of motion is now modified because now we have tau, which is acting here on the first joint, is some tau 0 minus k theta 1. So the idea is that there is a constant initial torque, but as theta 1 increases, the torque which the spring is supplying reduces. Okay. So there is an initial preloaded torque tau 0. We have chosen this number 1.96 Newton meter, and the spring constant is given as 0.1 Newton meter per radian. And what is the basic idea? That I don't want to keep on applying this constant torque, because if you go back to your basic mechanics, this torque will be something like I alpha. So if the torque is constant, alpha will be constant, but then integral of alpha, which is omega, will increase with time, and integral of omega is rotation, which is theta 1, that will be like square. So it will keep on increasing, okay, in a parabolic path approximately. So we don't want that. We want eventually that theta 1 should stop. So for this simulation, we assume that these are the masses and lengths. So for this rigid body 1, it is 1.241 meters. For the fixed length, it is 1.241. So both the crank and the base is 1.241 meters. The second link is 1.2, the third link is 1.2. So if you choose these kinds of link lengths, then it cannot, theta 1 cannot rotate fully. Okay, as I showed you in the picture before, after a while it will form a triangle and the motion must stop. So the masses are 20 kgs, initial crank is the heaviest, and all other links are smallest. So this is actually some numbers which were obtained from an actual physical device. Okay, so these are what are called as deployable systems. So you keep these links in a horizontal position, and then you go to space or somewhere else, and then we actuate the actuator, or you start giving torque due to a spring or a motor, and then it will unfold and it will form the triangle. So that is, there are many such applications where you start from a folded configuration and then you go to an unfolded configuration. So we want to know how does this 4-bar mechanism moves, okay, as it unfolds. So as the spring unwinds, body 1 rotates counterclockwise. The lengths are chosen such that theta 1 cannot rotate beyond a certain angle. So the bodies 2 and 3 will lock when they align, and the 4-bar will become a triangle. And if you go back to some statics, a triangle is basically like a structure. The degree of freedom of a triangle is 0. Okay, the number of links, the number of joints, and so on will be, you can see that the degree of freedom is 0 and it will become a structure. So here is a video of this 4-bar. So as you can see, these links are almost lying in the horizontal direction. Okay, so you saw this motion. So the basic idea is it starts up very fast, but then the torque is some tau 0 minus k theta 1. So the torque is reducing. So towards the end it slowed down, and then we form this triangle. So what else can we find out from once we have such a system and once we have solved the differential equations using MATLAB? What else can we find out? So what you can see is we can plot the various angles. So for example, theta 1 is this dark line. Phi 2, which was the second angle, is this dotted line. and then phi 1, which is the output angle, is like this. We can also plot the two Lagrange multipliers. Remember, this is a closed loop system. This has two loop closure constraints, and associated with those two loop closure constraints, we have two lambda 1 and lambda 2. So I can plot lambda 1 and lambda 2 as a function of time. And what you can see is after about some 12 point something seconds, these lambda 1 and lambda 2 go off to infinity. Okay. So what does it mean? That we do not have two Lagrange multipliers after some time. Okay. At that time, 12 point something seconds, 25 seconds exactly, theta 1 is 150.4 degrees, and this link 2 and link 3 will align, so they will become like 180 degrees, and theta 1 is approximately 150.4. At 12.25, the Lagrange multipliers go off to infinity. So if you go back and recall, the Lagrange multipliers are basically denoting some constraint forces. So what do we have? As this mechanism is unfolding, it is going from a 4-bar to a triangle. At some point of time, okay, these Lagrange multipliers go off to infinity. So the constraint forces are going off to infinity. Okay, and physically what it means is the mechanism can no longer rotate. So there is lot of internal forces in the second and the third link. And that is what this Lagrange multipliers going off to infinity is showing. So the useful thing in this simulation are the following, that I can find out exactly when this 4-bar will become like a triangle, when these two links will align and it will lock, and then we have a triangle, and that is what? Approximately 12.25 seconds. And then we can also find out what is the forces which are your joint should see at around 12.25 seconds. The simulations cannot proceed beyond 150.4 degrees. Why? Because it is no longer moving. It is a structure. It is a triangle at that point of time. So the second order differential equation is no longer valid then. It is not moving anymore. So the simulations are telling me what should be the time for deployment and also at what angle it will stop. So for different link lengths, this time and this angle will be different. So we can have various designs of this 4-bar mechanism if we are planning to use this 4-bar mechanism for some application where we want to deploy it. So we can try out these simulations in the lab in front of computer and then find out what is the time, what is the forces, and so on. And this is one of the goals or usefulness of simulations. I can give you some very good idea about what exactly this 4-bar mechanism, or for that matter any other multi-rigid body systems is going to do. Let's continue. Let us look at this simulation of the rolling disk. So the first simulation was 2-hour robot with no constraints. The second simulation of the 4-bar mechanism had this loop closure constraints, and then we had this Lagrange multipliers. In this third simulation, we impose what are called as non-holonomic constraints. So constraints involving velocities. So quickly, the generalized coordinates for this rolling disk are x, y, z, which is the center of this disk. There is a rotation matrix between this disk and this reference coordinate system, which is the z, x, y. Z because the first rotation is theta 1 about the z axis. The second rotation is theta 2, which is the tilting of the disk about the x axis. And the third rotation is about y axis, which is the spinning of the disk. Okay, so theta 1 is called heading, theta 2 is called tilt, theta 3 is called spin. If you have rolling without slip, the constraint is that the velocity of the point of contact is 0, and velocity involves derivatives of this generalized coordinates. In the case of loop closure constraints, there was no derivatives involved in the constraint. And these constraints of that point of contact velocity being 0 can be written in this form. This was done earlier also. So we had x dot as a function of theta 3 dot, theta 2 dot, and theta 1 dot in this form: rc1 theta 3 dot, rs1 c2 theta 2 dot, rc1 s2 theta 1 dot, and so on. And the z dot is minus rs2 theta 2 dot. Again, c1 means cos theta 1, s2 means sin theta 2, and so on. So these constraints can be differentiated and written in this form. Again, is repeating. We have done this earlier also. And then the equations of motion are given by q double dot is m inverse tau minus c minus g plus psi transpose lambda. The lambdas are the Lagrange multipliers introduced for these three constraints. We can solve for that lambda with this long complicated expression involving psi, m inverse, psi transpose, and then whole inverse, and so on. And then we can obtain the equations of motion, and they can be solved in MATLAB using ODE 45. So we will substitute lambda back into this equation. So we have second order equations. How many second order equations do we have? There are 6 second order equations because q is x, y, z, theta 1, theta 2, theta 3. So q double dot will be 6 of them. Okay, and then when you convert it into first order form, we will have 12 first order equations. In this case also, there are no external torques. This is simply rolling. Gravity is there, but there are no external torque. So if this was like a wheel with a motor here, then we would have to take into account the torque given by the motor. So that is a separate story altogether. So let us look at some simulations. Before we do any simulation, we have to assume some numbers, because any simulation software, we have to give some numbers. So in this case, we are going to assume that the mass is 0.5 kg, the radius of this disk is 0.1 meters, and then we need initial conditions for all the generalized coordinates x, y, z, theta 1, theta 2, theta 3 at t equals 0. So we have randomly chosen theta 1 0 as 45 degrees, theta 2 0 as 10 degrees, theta 3 0 as 0 degrees, x and y is 0 basically at the origin. So we are going to start at the origin. The z is tilted a little bit, and the z coordinate is 0.0985. Okay, so if theta 2 0 is 10 degrees, then theta 2 0 into cos and r. So this is very close to 1, but not exactly 1. And we also need initial conditions for theta 1 dot, theta 2 dot, theta 3 dot, x dot, y dot, z dot, and these are chosen here. So theta 1 dot is 0, theta 2 dot is 100 degrees per second, 200 degrees per second. This is 0.3684 meters per second. Y dot 0 is 0.1253 meters per second. Z dot is minus 0.303. So these have been chosen sort of randomly by trial and error, just to make the simulation interesting. So what do you think the simulation of this disk will look like, and how do we find out? So we basically need to solve the equations of motion. Okay, so this video is showing what the disk is doing. So as you can see, it is doing something reasonably interesting. Okay, and at every place at the point of contact there is no slip. So as you can see that the trace of this point of contact is very, very interesting. Okay, it will make these curves on the ground. We can also now plot the center of the disk, how it is moving, the y coordinate, the x coordinate. So this is the x coordinate, this is the y coordinate, and this is the z coordinate, and this is the way the z coordinate is changing with time. The simulation is for 10 seconds, so the z is sort of approximately understandable. It has come to 0, go back, up and down, it keeps on doing this. The x and y coordinates are much more interesting. We can also find what theta 1, theta 2 and theta 3 are doing. So this is a plot of theta 1, theta 2 and theta 3 in radians. So you can see there's some interesting plot as how the heading, the tilt and the spin of the disk is changing with time. How do we know all these simulations are correct? Okay, one test is that we need to ensure that the total energy of the system is constant. Remember, there is no external forces. So whatever is the initial starting energy, which is the kinetic energy and the potential energy, we know what is the potential energy. It is like mg into r cos theta 2. We know what is the kinetic energy. There is an expression for the kinetic energy which I have shown earlier. So the sum of kinetic plus potential energy should be constant, and we can plot that. Okay, so in this example, the red curve is that of the kinetic energy of this disk. Okay, some half I omega square plus half mvc square, and potential energy is some mg into some r cos theta 2. So the potential energy is the blue one, and the sum of both of them is this dark one, which is more or less constant. So this gives us some confidence that whatever the code you have written, whatever the simulations you have done, makes sense. Let's look at another interesting example of this rolling disk. So in this case, the initial conditions are different. Okay, so now we start with theta 1 0 as 45 degrees, theta 2 0 as 5 degrees, theta 3 as 0. Again, the x and y coordinates are starting from origin. The tilt is same, around the same, but then we give some initial theta 3 dot, initial x dot, initial y dot, and initial z dot. So we are going to give some motion to the center of mass of this disk. So let's see what this disk will do now. So what is the motion of this disk? So this is a plot which is obtained in MATLAB. MATLAB allows you to do all this simulation, also do this animation. So as you can see, it looks pretty good that we have this disk which is going around in this circle. It is also tilting a little bit because theta 2 is not 0. There is some 5 degrees initially. So it is roughly going around the circle, but it is also tilting in and out of from the vertical. Again, we can plot xc, yc, zc. So these are some plots which you have obtained from MATLAB. We can also plot theta 1, theta 2 and theta 3. So theta 3 is pretty much constant. It is going up. Theta 2 is like some oscillation, and theta 1 is also going in the opposite direction. And again, to check whether this simulation is correct or not, we can plot the kinetic energy, which is this red, which is oscillating like this, the potential energy, which is oscillating like this. So remember, the disk is not tilting too much. It was tilting a little bit, so hence the potential energy itself is very constant. Similarly, the kinetic energy is not going to change much. It is going more or less in a circle, okay, sort of like a constant speed with some little bit of perturbation. And the sum of both of them again is whatever is the initial kinetic and potential energy, and that is staying constant. Let's look at third simulation. This is a nice interesting problem, no? You can see all these nice motions of this disk. So again, here we have some other initial conditions. So basically Z now is some, initially it's 0.1 meter, okay? And then we have this some different initial theta 1 dot, theta 2 dot and theta 3 dot, and also different x dot, y dot, z dot. Okay, so it is not very easy to guess what this rolling disk will do with this initial condition. So let's find out. So it is sort of similar to the first case, but as you can see, it is doing this but not going at the same place. It is also moving along the y-axis. Okay, so it is moving in the x and z axis, but it is also moving forward. And we can do all this very, very nice simulation and animations in MATLAB. And again, we can plot this x, y, and z. We can also plot theta 1, theta 2, and theta 3. Okay, so this is theta 1, theta 2, and theta 3. This is x, y, and z. We can make these plots. And we can again check that the sum of the kinetic energy and the potential energy is constant. So again, the kinetic energy is shown here. This is the potential energy and the sum is this. And you can play around with these code. Okay, so the TA will put up this code in some available place. You can try it with some different initial conditions and you can see what the disk is doing. So in summary, after the equations of motion of a multi-body system are obtained, one can solve two problems in multi-body dynamics. One is, this is called as the inverse dynamics problem, which is that given trajectory as a function of time, find joint torques. Okay, this is just simple substitution on the right hand side of the equations of motion. And the next one is forward dynamics, which is given the joint torques, find the trajectory in time. Okay, and these are, I have shown you for the thin disk and even the 4-bar mechanism and even the planar 2R. So if I give some torques which are acting at the joint, what does the mechanism do? Okay, how does it move? The inverse dynamics, as I said, is straightforward. It is just substitution in the equations of motion. Forward dynamics involve numerical integration. So you have to go to MATLAB with some initial conditions and in the state space form, and then you can integrate. And I've showed you examples of the planar 2R, a 4-bar mechanism, and a thin rolling disk. These dynamic simulations can be done by computer tools. So right now we have derived the equation of motion and we have solved it in MATLAB. But we can also, without deriving the equations of motion, we can solve it in computer tools. And that is what we will discuss later.